Good morning, welcome to new lecture. In this lecture, I will explain the tensile test and how we will draw stress-strain curve, and I will define some mechanical property of the material. So let's see how we can find some important mechanical properties of material. And what does that mean, mechanical properties of material? Let's look at one, for example, rod or bar or a specimen sample we take from one material. Usually it is cylindrical shape. Later on I will talk about the dimension, but usually it is cylindrical shape. And we apply tension. So axial loaded bar, we apply force axially. P and P. So the only internal force in this rod, inside we will have P, because external load we are pulling with P. Assume this specimen or sample is from A36 steel. A36 steel, this is named in the ASTM. For those they don't know what is the ASTM, ASTM stands for American Society for Testing and Materials. So they call this kind of steel A36. This kind of steel usually they use in most construction. In construction, I-shaped beam, H-shaped column. Most steel we are using in construction, it is A36 steel. If we have sample from A, for example, 36 steel, I apply tension. What is the stress? The initial length, for example, it is L naught. The initial cross-sectional area, it is A naught. First assume we don't have any tension. So P is equal to 0. Then step by step I will increase P to the P1, a little bit I will increase more, P2, P3 and so on. So in each step I can define stress is equal to force divided by initial cross-sectional area, and strain is equal to deformation in that step divided by initial length. So in each step for P1, P2, P3, P4 and so on, I increase step by step gradually. So I can define sigma 1, sigma 2, sigma 3, epsilon 1, epsilon 2, epsilon 3 and so on. And I will show those points in one graph, one curve. We call it stress-strain curve. In stress-strain curve, the vertical axis will be stress, the horizontal one will be strain, epsilon. If we conduct this test on A36 steel, for example, we will end up with one curve, something like this. It will come like this, then like this, then like this. It will go up and come down, something like this. Let's I show different points on this curve with different color. Here is origin, point O. Then it will come linearly to here. I show with point A. Then it comes here, point B, point C, maximum point, point D, and point E. This we will call it engineering stress-strain curve. Pay attention. We can create another curve. They call it true stress curve. True stress curve, it will be similar to something like this. Why? Now I will explain. Dash the line. Okay. If we apply force, first the behavior is linear elastic behavior. Linear elastic means stress and strain. They are proportional. And if we remove the load, material will have initial size. So deformation will come back to the initial location. So no permanent deformation. That linear part. So from origin up to here, this part, they call it linear region. That's like linear region. Then from point A to point C, this part, they call it perfect plasticity. Or yielding region. From point C up to point D, here, this part, it is strain hardening. So this part name is strain hardening. Strain hardening. From the maximum point until failure point E, we call it necking. So linear region, perfect plasticity or yielding region, strain hardening region, and necking region. Let's define these points. Points A, we call it proportional limit or elastic limit. Of course, most of the time, proportional limit and elastic limit, it is the same point. Sometimes it is different a little bit, but in most example, elastic limit point, point A, proportional limit point, again it is point A. Point B, we call it yielding point. I will define all of those. Point D, we will call it ultimate stress point, and point E is rupture or failure point. What is this dashed line? Here pay attention to see what is happening. If I apply tension load to one bar, if I increase load, increase, suddenly I will see deformation in cross-sectional area. I will see the part of cross-sectional area, for example in the middle, decrease in local cross-sectional area. How it will decrease? It will turn like this. So, part of cross-sectional area suddenly will decrease, and it will get smaller and smaller. That part, that point is necking region. In this region, you see cross-sectional area gets smaller. Now for calculating the stress, what is the stress? Stress is, we define, load divided by initial cross-sectional area. But if we continue this test, we increase P step by step, gets bigger, suddenly we will see the necking area, the cross-sectional area becomes smaller because we have large amount of strain in a small region. In this region, we have large amount of strain. Because cross-sectional area, it gets smaller, the stress, here we can define a stress, we call it true stress. We can define force divided by the area of the section at that instant. So instead of dividing load by initial cross-sectional area, I can divide load to cross-sectional area at that instant. That cross-sectional area is smaller. So what will happen? Stress will get bigger and bigger, and we will have failure point here. This curve, we call it true stress curve. So that is the first difference. Let's define now this point. What is the proportional limit? So point A here is proportional limit, or we call it elastic limit. But we should define these points. I would like to write those points because it is important on the board. I define those precisely. So, proportional limit. Proportional limit transition between linear and nonlinear behavior. We call it proportional limit, elastic limit. Elastic limit is transition between elastic and plastic behavior. We call it elastic limit or maximum stress or we can call it maximum stress with full recovery. Another point is yielding stress. Yielding stress is the point strain continues with little or no increase in stress. So you see, strain continues with little or no increase in stress, and that takes place after after the elastic limit. Another point is ultimate stress. The maximum point in the stress strain curve, we call it ultimate stress. Maximum stress on the engineering stress strain curve Another point it is rupture stress. It's rupture stress point where specimen fractures. I would like to add, we have two types of material. We call it brittle material and we have ductile material. Some material, they are brittle material. Some material are ductile material. For example, what is the brittle material? If we apply force to the glass or concrete, we will not see a lot of deformation and suddenly we will see the failure. Those material, we call it brittle material. Some material, if we apply tension, before fracture or failure, we will see a lot of deformation. Those material, we call it ductile material. Ductile material, for example, is steel, for example, copper, aluminum, or for example, rubber. Those are ductile materials. Let's define those. So we can divide material into two categories. We will call it brittle material, little plastic deformation. Such a little plastic deformation before failure. Let's add here before failure. Such as glass or concrete. Ductile material, lots of plastic deformation before failure. Such as steel or rubber. So let's come back to our stress strain curve one more time and show the different points, because now we know the definition of those points. So if we have one specimen or sample, under tensile test we apply tension force. Assume we have this rod or bar, we apply force P, and we know stress is equal to force divided by cross-sectional area, and strain epsilon is equal to deformation divided by initial length. The cross-sectional area is A0, the initial length is L0. If we apply force and we increase force from 0 origin point, and we represent strain in horizontal axis and stress in vertical axis, then we will end up with one curve. Assume the sample we take from A36 is steel, so there is difference in stress strain curve for different material, because in this kind of steel, those points clearly we can mark it. So I use A36 steel. See what will happen. We apply force from 0 to P1, so stress is sigma 1, strain is epsilon 1. Then we will increase to the P2, P3 and so on. So we will end up with point epsilon, sigma 1, epsilon 1, sigma 2, epsilon 2, sigma 3, epsilon 3 and so on. If we show those points in this coordinate and we attach those points, finally we will end up with curve something like this. This is engineering stress strain curve. First, stress and strain, they are proportional, and relationship between stress and strain is linear, and if we remove load we will have full recovery in deformation, so we will not have any permanent deformation. This point we show with point A, proportional limit. Then we will have permanent, slightly small amount of permanent deformation, and material starts to show nonlinear behavior. The start point for that, it is point B, yield stress point. You see in this region we don't increase the stress. Stress almost is constant, but strain will continue to increase up to point C. So this region we call it perfect plasticity or yielding region. Then in order to increase strain, we should increase stress, we should add load. If we add load, we will increase the stress, and again strain and stress will increase together. So this region, we call it strain hardening up to here, this point. The maximum point on stress strain curve, we call it ultimate stress. Then we will have failure in one point, something like this. But this is engineering curve. Pay attention. If after increasing the load, as I mentioned, suddenly we will see cross-sectional area in one part of this rod, it gets smaller. In this region, if we divide force by area at that instant, instead of this curve, we will end up with another curve, something like this dashed line. This is true stress strain curve, so we call this true stress. This is about material behavior, and those points we call it mechanical property of the material. Of course, we have other points too later on, other mechanical property of the material as well. Later on I will define those again. This is about mechanical property of the material. Let's look at to the material behavior under temperature to see under effect of temperature what will happen in the material. So let's start new topic, temperature and its effect. I will call it temperature and its effects. You know, because of the temperature, the mechanical property of material will change. If we increase the temperature, what will happen? We will have expansions. If we decrease temperature from room temperature, what will happen? We will have contraction. For example, assume we have one steel bar in room temperature. I increase the temperature from room temperature. What will happen? We will have deformation and we will have expansion. The size of that bar will increase. If I decrease temperature from room temperature, we will see contraction. The size again will change, but this time it will get smaller. So temperature will cause expansion and contraction. So temperature will cause expansion and contraction. If material is free to deform, it is free to move, this temperature will cause expansion and or contraction, but we will not have any internal stress. For example, assume we have this bar. I increase temperature, the initial temperature, then let's give dimension for this. The initial length is L0, the initial cross-sectional area it is A, Young modulus is E, and temperature is room temperature T0. I increase the temperature, what will happen? The size will increase, we will have expansion. I increase temperature from T0 to T, which T is greater than T0. We will have expansion, size will increase, but because it is free to increase size, we will have deformation, cross-sectional area will increase, volume will increase, length will increase. But we will not have any internal stress in this rod. Any material, it is free to deform. If we increase temperature or decrease the temperature, we will see deformation. But we will not have any internal stress inside of the material because of the temperature effect. But if it is not free to deform, in that case we have another story. In that case we will not see any deformation or size change. But instead of that, we will have internal stress inside of the material. Let's write that here. If thermal expansions or contractions are resisted by some means, then thermal stresses will be produced. Okay. Assume we have this rod. I increase the temperature from room temperature. Size will increase and length will increase because of this temperature change as much as delta. So initial length it is L naught. After increase the temperature to the T, the length will be L naught plus delta. So what is the variation in the length? It is delta. How we can calculate delta? Delta is equal to alpha delta T times L naught. What is the alpha? We call it thermal expansion coefficient. Delta T is the variation in temperature. L naught is initial length. So we can measure how much length will increase. But if it is free to increase the length, in that case we will not have any internal stress or we will not have any thermal stress inside of that rod. But let's look at to another story. We will look at here to the two different scenarios. First one, it is the same rod. I attach to the wall using fixed support, and the length is L, cross-sectional area it is A, Young modulus is E, and thermal expansion coefficient it is alpha. I increase the temperature. The amount I will increase the temperature it is delta T. If I increase the temperature, we will have expansion, we will have deformation, and size will increase. If I decrease the temperature delta T, we will have contraction. Instead of increasing the length will decrease. It is the same thing, no problem in the behavior, only the direction of the deformation is different. Let's here, I define alpha one more time. Alpha is thermal coefficient of expansion. How we will define alpha? Alpha, it describes how the size of an object change with a change in temperature. It measures the fractional change in size per degree change in temperature at a constant pressure. So we call it thermal coefficient of expansion or coefficient of linear expansion. We will show with alpha. What is the unit for alpha? Unit for alpha, it is 1 over Kelvin or 1 over degree Celsius or 1 over degree Fahrenheit. This is the alpha unit. Alpha for each material is known value. There are tables. We can do simple experiment and measure alpha, but we have a lot of tables. especially you can find in the appendix of mechanics of material books. If you go, you get to the material name, for example, copper, for example, different type of the steel, brass or something, you will find alpha for that material. So if we know the material, we can find the alpha and we can measure it using simple experiment. Maybe in future I will explain that. Anyway, so alpha is known value. Let's come back to our example. If in this rod I increase the temperature, what I will have, deformation delta will be equal to alpha delta T L, and I show with another color here. If I show with red, I will have deformation like this delta, and because this rod is free to deform, we will not have any thermal stress inside of the material, only we will see the deformation. Assume it is the same rod, but this time it is between two fixed support. Here we have wall, here we have another wall, and this perfectly will fit between two walls, and we attach to those walls and it is perfectly fixed to the wall. I increase the temperature. What will happen? Again, everything is the same. Length is L, the cross-sectional area it is A, Young modulus it is E, thermal expansion coefficient is alpha, and I increase temperature delta T. What will happen? This rod wants to deform, but there is no space for deformation. So it cannot deform. We will not see delta. But instead of that, we will have internal thermal stress inside of the rod. How we can calculate that? It is easy to calculate. Here, if we want to calculate that stress, assume this is one end fixed, one end free. This example. If I increase temperature, what will happen? We will have deformation as much as delta, if it is free. But now we have wall, another support here. This support will not allow to have this deformation. What will happen? This support will apply reaction. That reaction, for example, I show with F. That support will apply reaction, and that will return deformation to the initial point. And finally, we will have zero deformation. If the deformation because of temperature is alpha delta T L, and because of that deformation, in this valve, we will have reaction. That reaction deformation will be FL over EA. This deformation from left to right, this deformation from right to left, they should be equal. If we put those deformation equal, alpha delta T